the words of great Austrian theoretical physicist Erwin Schrödinger. He used to say that consciousness cannot be accounted for in physical terms, for consciousness is absolutely fundamental. It cannot be accounted for in terms of anything else. With these words, let's hear on a topic called consciousness, sleep, and the quantum by Professor Antoine Suarez, founding director, Center for Quantum Philosophy, Zurich, PhD, ETH, Zurich, Switzerland. Consciousness, free will, and sleep and death are fundamental facts of physical reality and require a world that is quantum. Quantum physics brings in to light the crucial role of the observer in science. This amounts to declaring that consciousness and free will are prerequisites of science, and more precisely, as submitted to the limits of sleep and death. I will argue that sleep relates to randomness and death to irreversibility, and conclude that the world is quantum in order to fit with such fundamental limits. Sir, I will like to hand over the session to you so we can start our talk on consciousness, sleep, death, and quantum.
Okay, so let's start. Well, first of all, many thanks to Varun and Vasudeva, and certainly to the Bhaktivedanta Institute for inviting me to this exciting meeting on science of consciousness. And I am especially grateful that I can present you my view on this relationship between consciousness and the quantum. Let us start with some experiences of ordinary life. First of all, we observe in ordinary life everyday natural regularities. So, for instance, regularities that are determined by information in space and time and that are predictable. I can say that the sun in Kolkata on next Monday will rise at 5:12 and the sunset will be at 18:10. These are regularities that allow us to calculate, to predict the world, and so we can live in this world also comfortably. But there are other interesting experiences in ordinary life. For instance, the sleep-wake cycle that we experience every day and every moment and every night when we go to sleep. Here, for instance, when I am speaking to you now, I am consciously and freely ruling my bodily movements, my lips, for instance. What I tell to you is not completely predetermined, but contains information you cannot predict and hopefully is to some extent new for you. But nonetheless, my consciousness and free will is not absolute. They are interrupted and limited, for instance, by sleep. And there is a third experience of ordinary life. We experience this in our environment every day, death. The physicians define death as the irreversible breakdown of all the neural capability, but more specifically, the breakdown of the functions of the brain stem. And this means the breakdown of the neural capability for spontaneous movements. So, three experiences of ordinary life. How do these experiences relate to the quantum? Well, the quantum realm is characterized mainly by two main features. Quantum superposition that implies non-locality, I will explain this now, and the measurement problem. You know about this problem because you have surely heard about the paradox of the Schrödinger cat. Well, Let me say that when you hear expressions like collapse of the wave function, this is a characteristic and typical expression of the Copenhagen interpretation. You hear this rather cryptic expression, collapse of the wave function. What does this mean? And this, I give you, I think, a clear meaning of this expression. It conflates two different assumptions. Assumption A, this means that the decision of the outcome, which of the detectors counts, this will be clear now in the follow, happens at the moment of detection and involves non-local coordination between the detectors. And assumption B is that at detection, the outcome becomes irreversibly recorded and can be observed. This is the measurement problem. Let us see what means quantum superposition. I say quantum superposition implies non-locality, and this means at the end that the quantum realm is something beyond space and time. Suppose we have here this quite simple experiment, a laser source emitting particles, and if we assume, as Newton did, that light is made of particles, then this detector here will detect with this setup 100% of the particles. All particles will be captured by this detector. Now let us go to the setup B. In setup B, we have here a beam splitter. Part of the light goes transmitted, part of the light goes reflected. Then if we set here two detectors, then detector 1 will detect 50% of the particles, and this other detector, detector 0, will detect 50% of the particles. We complicate a bit more the setup. Instead, we make this, that the beam going transmitted will be guided by this full silvered mirror to this detector, and the beam going reflected will be guided by this full silvered mirror to detector 1. So the question is now, how much counts detector 1? How much count detector 0? Obviously, we have again the result 50% and 50%. Now, a bit more complicated setup. Here you set again a beam splitter like the beam splitter here. How much count detector 1? How much count detector 0? You will say, if we assume light is made of particles, the particle model of light, you will assume, well, here you have going, this beam will be split here in, and we will have 25% going to detector 1 and 25% going to detector 0. And the same for this other beam. So the reflected beam, 25, so 25, so. So if light is made of particles, if you assume the light model of particles, the Newton model, then here in this case you should also get 50% and 50%. Nonetheless, if you perform the experiment in the lab, the result is this one. You get detector 1, 100%, detector 0, 0%. So this means the particle model doesn't work. So this was the such experiments is what led to scientists like Huygens, Jung, and Fresnel to the wave model of light to explain interference phenomena. The wave model allow you to explain the precedent result, because if you have a wave going so, in this beam splitter, part of the wave will go transmitted and part of the wave will go reflected, but a bit shifted in the phase. You see, in the phase there is a shift. So what happens is the following. If you have here this setup, here you have light transmitted and then here reflected, and here you have reflected and then transmitted. One reflection for this and one reflection for this. This means there is at the end the same phase shift, and then the two waves arrive here in the same phase, and then they add constructively, interfere constructively. However, here you have transmitted and transmitted, and here you have reflected and reflected. So the two shifts and the reflections add, and then at the end here, in the going to detector 0, you have that the two waves are in opposite phase, and so they interfere destructively, and you get 0%. So you can even now change a bit this path length, and so you are changing the phase difference. And so you will get here that this detector is counting from 100% is going down to 80%. And this one, when you are changing here a bit, the path length is going from 0% to 20%. And you have this sinusoidal behavior of the counting rates. And this is the characteristic of the interference phenomenon. Well, you could say also, excellent, then light behaves according the waves model. Let us assume that it assumes like a wave. But you see, if light is like a wave, then this would mean that in this case, you will have wave here and wave here too. The wave is going all the ways. So you have wave here and wave here. Probably here you have a bit more intense wave, and here a less intense. But in any case, you should have waves all the time in this configuration, and you should have wave here, and this would mean that in this configuration, for all runs, the experiment will count, and this will count also. So this is the prediction. If you have, if light behaves like waves, then you have wave here and you have wave here. This means the two detectors should count jointly. But the experiment shows this is not the case. If one detector counts, that is the photoelectric effect, for which the explanation of this effect gave Einstein the Nobel Prize, then you see is that if detector 1 counts, detector 0 doesn't count, and vice versa. What means this? The photoelectric effect falsifies the wave model of light. So this is, you cannot explain light neither with particles nor with waves. So this is the entrance to the quantum world. You have interference experiments and photoelectric experiments. And these two experiments together mean that at the end, the wave, the light cannot be explained neither as by particle model nor by the wave model. This is the very entrance to the quantum world. So that is what I say. These two experiments together is the platform 934 to the quantum world. Similarly, are the platform 934 in the tale of Harry Potter. You see me here in King's Cross Station in London, entering the quantum world. Well, that is, we come again, this kind of effects, interference, photoelectric effect, is what led to this expression, Copenhagen expression, of the collapse of the wave function. Guys like Bohr, Heisenberg, and Born coined this expression. But at the end, as I told to you, this means nothing other than there is an agreement between these two detectors, an agreement about which detector clicks, which detector counts. Every time you send, you run an experiment with one photon, then there is an agreement of the two detectors, which of them counts. And then each detector knows how often he has to count. But in order that I count and the other detector doesn't count, it is important that there is an agreement. This is nothing other than the meaning of this cryptic expression, collapse of the wave function. Non-locality means precisely this: the decision of the outcome, which of the detector counts, happens at the moment of detection and by an agreement between the two detectors. So, you know, this explanation of the Copenhaganians led to a big debate in the Brussels Congress of 1927. You have here all these guys got the Nobel Prize here, which are here together. And this debate means that Einstein was against this interpretation. Why? Einstein came to the Solvay Congress with this experiment, the very simple thought experiment. You have light going through this through a slide. There is diffraction, and then so to say, the waves arrive to all this array of detectors. And now suppose that this detector here decides to fire, to count. But then all the others should remain silent. And this means that this requires a coordination between all these detectors. If I count, all the others don't count. When Einstein heard this sort of interpretation, he was quite upset, because this means that if you set these detectors far away, enough far away, then a coordination between the two detectors implies something, some kind of communication faster than light. And Einstein said this is against special relativity, and this means that quantum physics is not quantum mechanics at this time, is not correct and has to be completed, because the coordination means detector 1 counts, 0 doesn't count. If detector 0 counts, 1 doesn't count, and this implies a coordination. Without coordination, you would have that sometimes the two detectors will count together, and other times no detector will count at all. You see, this superposition between 1 and 0 before the detection, this is nothing other than the qubit. We come now to this. So you have here quite important principle of the quantum, is that not all what matters for physical phenomena is contained in space-time. You cannot explain this phenomenon of interference and photoelectric effect together. You cannot explain this by information propagating at the velocity of light, or lower or less. That is, propagation in space and time. You see, this is the idea is here of the quantum superposition. This means that before the system, before the detection, the system is described as being in superposition of getting of result 1 and of result 0. That is the wave function, so to speak, and the interpretation means that before measurement, the state, whatever it is not determined to give 1 and to give 0, but it can give 1 with a certain probability. The probability is given by this coefficient here. The square of this coefficient is 1/2. This means 50% of times you will get result 1, and 50% of times you will get result 0. But when detection happens, this means in this moment there is this instantaneous coordination between the detectors. You know, this kind of description by a superposition, that the state is in a superposition before measurement, that is nothing other than the qubit. And the very basis of, for instance, quantum cryptography, quantum computing. Quantum computing is working with the qubit. This means with this sort of superposition between two bits, two classical bits. The qubit is the superposition of two classical bits. So the Bohr's rule generalize this simple experiment of before for any other situation. When you can change here, then you are changing here this coefficient, you know. And so in squaring C1 square root of 2, if you square this, then you are getting these different probabilities here, 53%, 47%, and so on. You can, by the Run's rule, give you the probability of each result for the different configurations, and then reproduce this sinusoidal behavior of the counting rates. The important point here is the following, is that suppose that each time you get 1, you note here 1. And if you get here a 0, then you get here, you write here 0. So if you get one detector 1 counting, you put here in your sequence here 1. If it is the detector 0 that counts, then you introduce here a 0. So at the end, you will get, after many runs, millions of runs, you will get a very big bit sequence. And no, what quantum physics allows you to do is to calculate how many % of 1 you will get here and how many % of 0 you will get here. But quantum physics is not capable of predicting. Science cannot give you any rule to predict which order you will get here, which precise bit sequence you will get here. This is beyond what science can predict. And you could say this bit, this string of bit, this bit sequence could very well contain the information of a masterwork of literature or music. This could be possible, and nothing speaks against this. In the long term, you have to have the prediction, the distribution of counts predicted by quantum physics, but how long must this be? How long is this long term? This quantum physics says nothing about. So you see, this means that actually brains can be compared to quantum devices. Now, when I am speaking to you, I am producing a bit sequence, a long sequence containing an information, and the parameters of my brain can predict a certain distribution of ones and a certain distribution of zeros, according to the physiological parameters. But now I am controlling consciously this sequence, and I am producing information, and that is why you heard me to tell you things that are more or less sound. Well, that is the problem, that I am now controlling consciously the outputs of my brain. And this is what I'm telling to you is not a masterwork of literature or music, but this is sound information, controlled information that is now, because I am conscious, controlling the outputs of my brain. Now, what means this? This means that when I'm sleeping, I have no this conscious control, and then there is sort of a random firing of the neurons, so that this randomness means that there is the neurons fire according to certain physiological parameters, but there is no, in this moment, I am not consciously controlling the outputs. And that is, you see, quite important is that when I am telling to you no, I am controlling the outcomes of my brain, and in a sense, I am deviating probably from the distribution of quantum physics. But this doesn't violate any rule of nature, because this is quite possible, because it is only what I'm now controlling deviates a moment from this distribution, but then when sleep happens, then this distribution is coming again to the predicted by quantum physics. So in a sense is that sleep introduced the randomness in my conscious behavior. So you can illustrate this by this nice cartoon. Is a random number generator telling 99999. Are you sure that this is random? Well, the problem with randomness is that you can never be sure. So this is a very, I think, very good illustration. This means that random behavior is sort of unconscious voluntary behavior. And when you introduce consciousness to this basic voluntary behavior, then you are not violating the quantum probabilistic laws of nature. So you can say conscious purposeful behavior limited by randomness, or what is the same, consciousness interrupted by sleep. This is an axiom of quantum physics, you see. Consciousness and free will are first in the logical order. I am not deriving consciousness and free will from the quantum, but rather the other way around. The quantum derives from this axiom that we should have limited consciousness and free will in the world. Our world must allow for consciousness and free will, but these important two commodities are limited. And sleep is the very demonstration that brain is not a device to produce consciousness, but is a device to limit consciousness. Still an illustration. Consciousness means awareness of personal identity. Though I am rooted in space and time, I am invariant in time. I am the same person and author now as when I have proposed quantum experiments with moving measuring devices 25 years ago. The conservation of personal identity is the very foundation of copyrights, and to these copyrights we all keep to them. First claim of my presentation, the sleep wave cycle requires a world ruled by quantum superposition and randomness. And the sleep wake cycle is this axiom of, of limited consciousness and free will. Now, there is a century of experimental evidence supporting non-locality and detection. I have to make here a very quick survey. We can go in details in the discussion, and I mentioned two experiments where I have been involved. You see, one is the realization of the thought experiment by Einstein in 1927. Amazingly, this experiment was first done in 2012 by this team in the lab of quantum optics of Geneva, and it consisted, as Einstein proposed, to put the two detectors, in this case we have only two detectors, to put detectors enough far away so that you can be sure that they cannot communicate when they count, in the moment of counting. And the result confirms quantum physics. That is, if you put the detectors far away, then you have still one detector counts and the other detector doesn't count. You could object, well, the experiment could easily be explained without invoking coordination, instantaneous coordination at a distance, because the detector, you could explain this way. If this detector clicks, this means that in the beam splitter, the particle went this way. But this is the explanation by Einstein in 1927, the explanation inspired by the Louis de Broglie empty wave. He said, well, it could be that there is a particle going wrong, and here there is a ghost wave. So in this case, the decision that this detector clicks is already here. You don't need any coordination here, but you need a ghost wave, a wave which is not material at all, ghost wave. So you can have locality, as Einstein wanted, but with the ghost wave. No, this is already a funny wave, an odd wave. But so this explanation, this is what led to this idea of Einstein. Quantum mechanics is not completed and there are hidden variables. Well, that is, in this case, you would get here the count, but Einstein went for reflecting, and then it came to invent the famous EPR paradox published in 1935. This is that instead of only experiments with one particle, you send particle pairs. This source emits one particle this way, the other particle this way, and then you will say, in this case, even if all is predetermined, you can say the photons are like genetic twins that are programmed by leaving the laser source. They are programming, and so consider only this part of the setup. then you will say you can get this here 50% of the times, or here 50% of the times. Well, and the other way around here, no? Okay, 50% of the time, 50% of the time. Then, if there is only local influences working, then you just say you can have this detector firing here and this detector firing here, or this detector counting here and this detector counting here, and same way for this other. This detector counting here and this counting here, or this detector counting here and this counting here. 25% of each possibility. What tells us quantum mechanics and what is the experiment, what is the result of the experiment, is that you get only these two possible results, perfected correlated, you see? So you cannot, with introducing ghost wave, you cannot escape locality. You come here with pairs of particles. With the EPR thought experiment, quantum physics are predicting also non-locality, non-local instantaneous coordination of detectors at both parts of the setup. So the two possibilities are illustrated here. And well, you know, this you can then change if you are making these experiments, in this case with polarizers oriented this way. If you change the orientation of the polarizer, then you will get here again the sinusoidal behavior characteristic of interferences that you got with the other setup I have shown you. And so by changing the angle of one polarizer, then you get different distributions of counting pairs. The guy that is decisive for deciding between Einstein explanation and quantum mechanics and the orthodox Copenhagen explanation is John Bell. John Bell had the idea and had invented the mathematical possibility to describe locality so that you can decide between Einstein and quantum mechanics. If I am speaking to you now here, is because in 1990, some months before the death, before John Bell died, I organized with him and at the CERN this colloquium on indeterminism and non-locality. This has been registered, bad quality video, but it is registered. You find this in internet. If you search for John Bell indeterminism and non-locality, there is a video at the site of the website of the CERN. You can get Bell explaining his theorem. Well, I cannot enter here the details. We can go, if you are interested, go in the discussion. Bell's theorem allows to distinguish if Einstein has right and the photons are calling, so to speak, hidden properties to produce the result at each part of the setup, then at the end, with this special setup, you have 16 possibility or 16 types of photon pairs. 16. And so you can, that is an exercise that you can make this in the grammar school. Even you can get 16. And so you can, it is an exercise of accounting. And then you can build a quantity S, and according, if Einstein has right, and the photons are going away from the source programmed, then S should be not larger than 2 in absolute value. And quantum physics predicts that S in certain with certain configurations, S is larger than 2, is larger than 2 by a factor square root of 2. This is Bell's theorem. Bell find the wave, the quantity S, to distinguish if nature behaves locally, then S has to be lower than 2. If nature behaves according to quantum mechanics, then S will be sometimes larger than 2. You see, this experiment is the experiment that performed by Alain Aspect in the 80s, and this experiment is the experiment that got the Nobel Prize in 2022. Well, actually, the Nobel Prize here is who really, well, the experimenters merit the Nobel Prize, but first of all, John Bell. Now, John Bell died sadly in 90. So the Nobel Prize gone to Alain Aspect, and let me see then what I have contributed to this entanglement experiment is that in this colloquium at the CERN, John Bell say this very clear: correlations cry out for explanation. And I asked him if it is then possible, if we should then say that relativity and quantum mechanics are incompatible. And he say, well, I think I can say that. He say, I think someone will put them together one day, and we will see that our imagination was too limited. Well, this, I was very inspired by this, and then I come to the idea of proposing, sort of experiment, but with a relativistic configuration, so that the beam splitters or the measurement devices are in movement, are traveling away from each other, traveling away from each other. Well, so that you have this relativistic configuration, and then the decision here, you see the decision here, that is the simultaneous timeline. The decision here in time happens before this, you see? But if you are moving, then the simultaneity line is this one. And then the decision here is also before the decision here. So the decision at every part of the setup happens before the other part. And this means that each decision cannot take count of the other decision. And if this is the case, the correlation should disappear. That is the before experiment, realized again in Geneva. Well, let me see, that is still an interesting picture. This experiment was financed by a private banker of Geneva, Lombard, that is Marcel Audier. And here we are in Innsbruck with Anton Zeilinger. Anton Zeilinger was also Nobel Prize laureate with Alain Aspect 2 years ago. We were discussing with him the possibility of performing this experiment before in his lab. Well, it was not possible because they had not the setup they were using with polarizers could not realize this configuration of measurement devices in movement. So the experiment before was at the end eventually realized by the group of Nicolas Gisin at Geneva, and sponsored by a private banker of Geneva by
Please,
Marcel.
sir.
Hello?
So please excuse me. The allotted time is over. So kindly, you are requested to kindly conclude the discussion at the earliest.
Okay, then let me see. The before experiment confirms quantum mechanics. This means we have to keep two influences coming from outside the space and time, and this was the reaction in the popular press. Now, the reason of all this is that the quantum realm is beyond space and time. And here you have the 60 years celebration of Nicolas Gisin, and stating that we have to keep something of intelligence, of invisible intelligence, ruling our world from outside space-time. Nicolas Gisin spoke in this on this occasion from angels. Well, there is the free will theorem also confirming this. So we can say that to summarize, if you accept free human beings, we have to assume free human beings outside space and time. Now, the second part of my talk, this should be to introduce you to the measurement problem and the Schrödinger cat,